Continuing problem 3 with questions C and D. So C asks us if we were to release block M 1.5 meters above the bottom of the triangle, find its speed at the bottom. And then D, assuming that there was a coefficient of sliding friction of 0.2 from the initial part A problem, how would that affect the acceleration? For part C, we have to use kinematics in this problem. In many cases, we can use conservation of energy, use mgh equal to 1/2 mv squared. But if you do that way, you have to take into account that the other mass, little m, is also being pulled and also changing its potential energy and its kinetic energy. So we have to be careful with that. So we're going to choose actually to use kinematics here. So the total distance that the block is actually going to slide down the ramp is 1.5 meters, or the opposite side, over sine of 60. So we're using sine SOHCAHTOA, opposite hypotenuse. We're trying to solve for the hypotenuse, and we get 1.73 meters. So that's our total displacement. We already know the acceleration down the ramp from part A is 5.4 meters per second squared. We know the mass, big M, starts from rest, V naught equals 0 meters per second, and we're solving for the final velocity. So we look at our equation sheet, and we have to use v squared is equal to v naught squared plus 2a delta x. We know nothing about time, and we're not looking for time, so that is why we choose the equation we do, and we get an answer of 4.3 meters per second for the velocity at the bottom of the ramp. Now for part D, it's asking us about, okay, well, if we have a coefficient of kinetic friction or sliding friction of 0.2, how's that going to affect our answer from part A? Well, because there's friction, we should assume that the acceleration is going to decrease, and if we look at the answer already, it does, but let's figure out exactly how we get there. So just like part A, we know that there's a parallel force of gravity for both the big M and the little m. Now I'm going to decide as down and to the left as being positive and down and to the right as negative when we set up our equation. So we already know force of gravity parallel for both masses act down the ramp respectively. But now we got to think about the friction, the frictional force between the two. So if the system is moving down in the direction of capital M, friction always is the opposite direction of motion. So because it's accelerating or moving in general to the left here in this system, then we know that friction on big M is going to be up the ramp, but the friction on little m is actually going to be down the ramp in the same direction as its perpendicular, or excuse me, parallel force, because again the system is moving to the left in the direction of the big M. So I define that again as positive. So FG parallel for big M minus FG parallel for little m, just like from part A. But now we got to subtract two frictions, friction from big M and friction from little m. Again, those frictions are going in the same direction, in the negative direction. And again, that's equal to the mass of the system times its acceleration. So we were reminded that force of friction is mu, which is the coefficient of friction, times the normal force. Now in this case, the normal force, when we're dealing with the ramp, the normal force is Fg perpendicular, or mass times gravity cosine of theta. So the little mass, we're going to use sine of 45 because that's the angle. And then for the big mass, 8 kilograms, we're going to use cosine of 60 because that's the angle of that side of the ramp. And when we plug everything in, we ultimately get an answer of 4.34 meters per second squared. For number 4, we have two clay balls that are moving towards each other, and they collide perfectly inelastically, which means they stick together, so energy is not conserved for inelastic collisions. So we know M1 is moving at 6 meters per second at an angle 45 degrees with respect to the vertical, and M2 is moving at some V2 60 degrees with respect to the vertical. So they're both heading down, but they're heading towards each other, one to the right, the other to the left. So part A is asking us what is the velocity v2, then B is asking us what is the velocity prime, or the common speed of the clay balls immediately after the collision. and then how much kinetic energy was lost as a result of the collision. So let's look at part A first. So since that final velocity of the two combined after the inelastic collision is vertical, that means the momentum in the x direction for mass 1 plus the momentum in the x direction for the second mass has to equal 0 since they cancel out. So we reminded that momentum is mass times velocity. So 200 grams times 6 sine of 45, because that's the opposite side. If we look at our picture above, the opposite side of 45 is my x component, minus 100 grams times v2 sine of 60, and that v2 sine of 60 is the total initial horizontal velocity of mass 2, and that all has to equal 0. Now we can use, since we're looking for velocity here, you might be asking yourself, don't we need to convert to kilograms? Not if you're solving for velocity, because ultimately the mass you're going to be dividing off by the mass anyways, so it actually does not matter. But if we were looking for the actual momentum, momentum is kilogram meters per second, so then we would need to convert. So just be careful with that and understand why we just used grams here and didn't convert to kilograms. But to be on the safe side, if you're not sure, go ahead and convert to kilograms. So anyways, we get an answer of 9.8 meters per second. So that's how fast that M2 is coming into the collision. Now for part B, we know again it's an inelastic collision. So initially, both set of masses are moving in the downwards vertical direction, and then they continue moving in the downwards vertical direction. So just like above, except now we're looking at the y component. So 200 times 6 cosine of 45, because cosine of 45 for the M1 is the adjacent side, which is the vertical component in the downwards direction, and we'll call that downwards direction positive for this problem, plus 100 times 9.8, since now we know how fast it was initially going, cosine of 60. And that equals the total mass combined, because again they stick together. That's what inelastic means, or perfectly inelastic, times v prime. That is the final velocity of the two. So we go ahead and do a little algebra, and we get 4.5 meters per second. For part C, it is asking us how much kinetic energy is lost in the collision, and this is actually proof that that energy is not conserved during inelastic collision. So we know that kinetic energy is 1/2 mv squared, and it's important to note that that energy is a scalar, not a vector. So that means we don't have to worry about making stuff positive or negative, because again, it's a scalar. It's just the magnitude. So initially, Ki, we'll call it the 200 gram mass. Now in this case here, we got to convert to kilograms, again, because we're looking for kinetic energy, and that's mass times velocity squared. So it's kinetic energy is measured in joules, but really that's kilogram times meters squared per second squared. So that's why we convert. So we got mass 1 plus the initial kinetic energy of mass 2 gives us 8.402 joules. Now after the collision, because they stick, we combine it as one big hunk of mass of 0.3 kilograms times its final velocity v prime from part B, 4.5 meters per second, and we get 3.08. There's a difference between the two, so clearly that tells us how much was lost. So the difference in those two is 5.4 joules, so that's how much energy is lost during the collision. Question number 5 is an electrostatics problem where we got two charges, or two masses, with each with a charge positive q, some distance away from each other. So this is essentially the balloon lab that we did in Unit 9. So Part A we're actually going to skip, because AP Physics 1, the curriculum does not include electric fields. So Princeton wasn't sure about that, so they included it in this problem, but you will not see that on the AP test. And then we go on to Part B then. So on the following diagram of Object 1, draw and label force vectors to represent the forces on the object. So of course there's a force of gravity, because it's a mass hanging from some rope, from some string. So force of gravity is down. Now we're looking at mass 1, so because they're like charges, they technically repel each other. So force, electrostatic force is to the left, and then the tension is up and to the right. As we can see, that's the direction of the string. Now the angle theta is measured from the vertical, so actually that angle with respect to the horizontal, as we see in the diagram in part B, is actually 90 minus theta. Now you don't need to include that in a free body diagram, but you should definitely have all three of those vectors as well as have them labeled appropriately. For part C, we're trying to find the tension in the left-hand string, so we're actually going to use our free body diagram from part B to kind of help us with that. Now, because this mass is in static equilibrium, meaning it is not moving, we know that the horizontal tension, Ftx we'll call it, minus the electrostatic force going in the opposite direction here, have to equal 0 because, again, it's in equilibrium. Now, first let's derive an expression so we don't have Ftx. Let's write it in terms of just Ft. So Ft adjacent side, so cosine of 90 minus theta. Well, cosine of 90 minus theta is the same thing as sine of theta itself. So if you think about it from a trig standpoint, that's true. Like, for example, cosine of 60 is the same thing as sine of 30. Right, 90 minus that angle is the same as using sine or cosine, just the opposite there. So we can rewrite this as Ft sine of theta. So we plug into our original equation, Ft sine of theta equals kq squared. So electrostatic force is kq1 q2 over r squared. But again, because they're the same masses, we'll just replace that with q squared over radius squared. Now that radius is the separation distance between the two. Now if we look, we don't know too much about the separation distance, but we know the length of the string is L, and we know that that the distance from the charge or the mass 1 to the vertical would then be L sine of theta. Now we want to know the distance between the two objects, so that's really 2L sine of theta. So that's where that denominator comes in, 2L sine of theta, again squared. So you do a little bit of algebra, so Ft sine of theta equals kq squared over 4 L squared sine squared theta. And you ultimately, when you solve for Ft, divide by sine theta, so you're left with kq squared over 4 L squared sine of theta squared.